In this video, I want to introduce you to constitutional isomers. During the course, you are going to encounter a couple of different types of isomerism, and they fall into two groups. They fall into either constitutional or geometric. We'll talk about geometric isomers a little bit later on in the semester. Today we're just going to cover constitutional isomers. So, what are constitutional isomers? Well, these are molecules that have the same molecular formula, but a different connectivity. Let's just look at a simple example. C4H10. This is our molecular formula, and it turns out that there's a couple of different ways that I can put C4H10 together. I'm going to have 4 carbons, 10 hydrogens. So let's just draw 4 carbons in a row. 4 carbons in a chain. And just to remind you, this is our skeletal representation. I will just count up the carbons. I'll highlight them in green. So we have 1, 2, 3, 4. And then if we consider the number of hydrogens we have in this molecule, I'm just going to write the number next to the carbon. Here we have 3, 2, 2, and 3. So I have 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. So we have the right structure that fits this molecular formula. And it turns out that there is another way that I can put together 4 carbons and 10 hydrogens. I don't have to put them all in a row or in a 4-carbon chain. What if I had a 3-carbon chain and then I added a 1-carbon branch? Does this still fit my molecular formula C4H10? Well, let's see. 1, 2, 3, 4 carbons, and let's go ahead and figure out how many hydrogens we must have. Here I have 3, here I have 3, here I have 3, and here I have 1. So I have 3, 6, 9, 10. So this also fits in with my molecular formula of C4H10. Let's look at another example. Let's do C5H12. Well, I always think that the easiest way for me to generate constitutional isomers is to start with a continuous chain that contains all of my carbon atoms. So in this case I have 5. Here we have 5 carbons in a row. 1, 2, 3, 4, 5. Let's think about the number of hydrogens that we have. And I'm just going to write the number 3, 2, 2, 2, 3. So I have 3, 5, 7, 9, 12. So I've got all of my atoms accounted for here. That's my first constitutional isomer. When I'm drawing constitutional isomers, the next step that I like to take is to draw a chain that's 1 carbon shorter than the one that I started with. So let's go with a 4-carbon chain and add a 1-carbon branch. This structure is also C5H12. I'm not going to add up all the carbons and hydrogens for you. I'm going to let you do that on your own, but just trust me that this is C5H12. Now, I want to point out to you that all of these structures that you're looking at right now, all the structures that we've drawn, these are all hydrocarbons. So what do I mean by that? Well, a hydrocarbon is a compound that is composed entirely of carbon and hydrogen. We have no heteroatoms. And remember, by heteroatoms, I mean anything that's not carbon and hydrogen. So these are composed solely of carbon and hydrogen. And also I want to call your attention to the fact that they all fit the general formula CnH2n plus 2, where N is the number of carbon atoms. All right, so N can be any integer. And if you put 4 into this equation, your 2n plus 2 is going to add up to 10, so that's our C4H10. If you plug in 5, 2n plus 2 will add up to 12. So any hydrocarbon that you draw that does not have any rings or any double bonds or triple bonds is going to fit this general formula, CnH2n plus 2. So if you look at these molecular formulas that we've started out with, C4H10, and you plug in the 4, right, and your number of hydrogens turns out to be 10, you can conclude before you even start drawing these isomers that you're not going to have any rings or any double bonds. Let's continue with our C5H12 now. So I drew a 4-carbon chain with a 1-carbon branch. Well, can I put that branch somewhere else? Do you think that I can put that branch somewhere else on my 4-carbon chain? Let's try. How about this molecule? Well, it turns out that this isn't new. This molecule is the same as this molecule right here. All I have to do is take this second molecule that I have drawn and rotate it 180 degrees, either clockwise or counterclockwise, and that's going to give me the molecule that I've already drawn. So if I can rotate the molecule in the page and come up with an isomer that I've already drawn, that tells me that those two are the same molecule. So that's not going to work. Well, how about if I put my 1-carbon branch at the end? Oh no, that doesn't work because this is the same as this. So I can't put the branch at the end. So I've exhausted all my possibilities for a 4-carbon chain. What about a 3-carbon chain? There I have a 3-carbon chain. Now I need to add either a 2-carbon branch. I can't add it to the end because that'll give me back my first structure, my 5-carbon chain. What if I add the 2-carbon branch in the middle? Well, actually, if I do that, that's not going to work out for me because that is going to give me back this. Right? These two things are the same. How about if I add 2 1-carbon branches to the middle? Yeah. And there we have it. We have a new structure that fits the molecular formula C5H12. And these are all of the structures that I can draw, all of the constitutional isomers that I can draw for the molecular formula C5H12. Why don't we take a minute and look at their condensed formulas. Now my first one is going to be CH3, CH2, 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 CH3. I could also write that CH3, and then in parentheses CH2, and there are 3 of them, followed by CH3. Remember that I can't do the subscripts, so all those numbers are supposed to be subscripts. So there we have our condensed representation for our first constitutional isomer. Let's try the second one. Starting from the left, I have CH3, then I have CH. My second carbon's attached to a hydrogen. It's also attached to a methyl group, a CH3 group. And I have CH2 and CH3. Another way that I could do this is CH3, CH, and then I could put my methyl group in parentheses. That makes it a little bit easier to interpret. CH2, CH3. So here's our condensed representation for our second isomer. And let's do our third. In our third, I have 1, 2, 3, 4 CH3s all attached to the same carbon. So I could represent that as CH3, 4, and then C. So that would be my condensed representation for this particular constitutional isomer of C5H12. And let's look at C3H6. Does this fit my general formula for a hydrocarbon with no double bonds and no rings? Well, let's plug in a 3 into this equation, 2n plus 2. That would give me 2 times 3 is 6 plus 8. So if I had no rings and no double bonds, that formula should be C3H8. So what this tells me is that I'm going to have to introduce a double bond or a ring. So again, I like to start by drawing a continuous chain, 3 carbons with all of the carbons in one chain, and there we go, and that would be C3H8. So I know that what I'm going to have to do is introduce a double bond into this structure, into this molecule. And let's look at this a little bit more closely. Count our carbons, 1, 2, 3, so I have the right number of carbons. Let's go ahead and just add in all of our hydrogens. 1, 2, 3 here. This particular carbon right here is showing 3 bonds, so I know that I'm going to have to add one more. That's going to be a bond to a hydrogen. And this carbon right here is showing 2 bonds, so I know that I'm going to have to add 2 more to satisfy the valence of carbon. So there we are, we have C3H6. Turns out there's another way that I can arrange C3H6. I can arrange my 3 carbons into a ring. So let's analyze this structure a little bit more carefully. I have 1, 2, 3 carbons. Let's go ahead and add all of our hydrogens. This carbon, and this carbon all show 2 bonds explicitly. So that means to each of those carbons I'm going to need to add 2 hydrogens. Let me go ahead and draw them in. So there we have our second isomer, our second constitutional isomer of C3H6. Unfortunately, there's not a formula that I can give you that will allow you to calculate the number of constitutional isomers that you can draw for any given molecular formula. It's really a matter of trial and error and exhausting all of the possibilities. Let's do C2H6O. Again, the way that I like to start is by putting all of the carbon atoms in a row. So I'll do that. There's 2 carbons. Then I'm going to attach the oxygen to one of the carbons. There we go. O. Let me count up the hydrogens that would be on these carbons, and I'm just going to write in the number. Here I would have 3. Here I would have 2, so that's 5. And if I look at this oxygen's not happy. Remember that oxygen wants to have 2 bonds, so what I'm going to do is I'm going to give my last hydrogen to that oxygen. So there is 1 constitutional isomer for C2H6O. There's another way that I can draw this. What I'm going to do is I'm going to rearrange the order of the carbons and the oxygens, and I'm going to put the oxygen in the middle. So here's my second constitutional isomer for C2H6O. I have a carbon here, and I have a carbon here. And let's think about the number of hydrogens on each carbon. I would have 3 and 3. So that's a total of 6. So this does fit the molecular formula C2H6O. And these are all of the constitutional isomers of C2H6O. Now it's your turn. And I want you to try C5H10. And I'll give you the answer in the next video.